Or okay. Okay, let's continue. So the first part of the class, we had a guest speaker. Hopefully that was useful for you guys. We might have one more. Uh, well, let me know that at the end of the class when we are doing the evaluation, whether you like it or not, and whether you want us to continue in the future. But I generally feel like it's good to have some perspective from other people, especially those who are in the industry. All right. Is there any question about the course computer assignments? I've seen that people start asking questions start early. Yeah.
Is it possible to like have a walkthrough of maybe like the first 5-10 cycles for like one of the traces? Just because I feel like a lot of the design decisions in the spec are not super clear about like exactly why is this happening during this cycle. So is it possible to have like at least an explanation for maybe the first like 5 to 10
I think I like for like shooting like a video and showing like what's happening.
Yeah.
Yeah, I can do that. I think part of the design is actually for you to kind of like go through and see, because I've seen people like going through and see some inconsistency and ask questions, which helps. But I think it's actually if you go over it and kind of see whether the algorithm that you think it's the same as what it shows, it's more helpful. But I can definitely answer questions like like go over it and see, for example, oh, you are scheduling it in cycle 5. But then it's like the spec shows cycle 4, like why? And then you can ask that question and then we can clarify it for you. Rather than you just watch the video that we say, okay, this is cycle 4 and this is cycle 2 and so on. But again, if you're still struggling more, I can definitely help. We can also sit together and then do it together if you want. Okay. But yeah, it's generally so there are quite few assumptions. The way to do it is it's a big design, right? So you have to kind of like start like peeling it off, right? Like one by one. So don't be overwhelmed with like the complexity of the design. Start from like some basic design. Okay, I need a instruction queue, I need a functional unit, there's some scheduling involved, right? Try to create some skeleton. Go through it, and then you will see that okay, now I need to add more details and so on and so forth. So that's how I usually do it. You can also like try to kind of like lay out all the details at first, but that typically takes a lot of time for you to kind of even get started. I rather to kind of like create some skeleton code and like do some simple things and then see whether my algorithm works. So for example, like your scheduling, right? So like that's the first thing. But there's like a bunch of checks that you need to do, right? So this is a little bit complex. So that's why you need to start early and you need to work on it. Okay. All right. So today I want to talk about cache. So we kind of done with the CPU microarchitecture. We kind of covered the front end and the back end. We talked about security issues. We talked about advanced, transient attacks and defenses. And then in the next two presentations on Wednesday and the next Wednesday, we're gonna discuss the papers. But I think we kind of covered, good amount about the microarchitecture, and then as you will do the project, hopefully things will gel all together, and you kind of have a solid understanding. Hopefully by the end of kind of like the mid-quarter, like half of the quarter, we have kind of spent a good amount of time on the CPU. Now it's time to kind of move on to the other very important aspects of a computer system, which is the memory. We kind of like talked about memory a little bit a few weeks back when we were talking about cache and cache side channels. I'm going to talk today mostly about just advanced features. So this lecture is not a security related lecture. And the next lecture, we're actually going to talk about the security issues in the memory. So we're going to give you a little bit of background on the cache and advanced issues in the cache. Next time, we're going to actually talk about some of the problems. We already talked about some of the problems already. So kind of to remind you, this is what you have seen, that generally important aspects of any modern system is a memory hierarchy. The reason that we need memory hierarchy is that smaller memories are fast, but they are small, right? And then bigger memories are obviously big, but then they are very, very slow. So what should we do is creating this sort of a hierarchy where the data that you use the most, if it's here, then you can kind of like access it as fast as possible. And then the data that you have here, if you only occasionally access this, then you kind of like 99, if you 99% of the time you are here and 1% of the time you are here, then the delay that you're going to observe is 99 times the delay of this versus plus the delay of this one, right? So the weighted average kind of like significantly be skewed toward the faster memory, right? So the whole business of memory hierarchy is that, can I bring this data as close as possible to the CPU? Of course, you cannot always do that for two reasons. One is you have limited size. So if, for example, quote unquote, what we call the workload that you are working with, it just happens to be bigger than that M1, there's nothing you can do, right? So for example, if you need to work always with 200 kilobytes, 200 kilobytes of data, and your cache, like L1 cache, is only 32 kilobytes of data, then there's nothing you can do, right? It's just your workload is large. This is just generally a small system. The only way that you can speed this up is having bigger memories, right? But if you, for example, only using 30 kilobytes of memory and you have a cache of 32, so you technically can be intelligent and smart about how you kind of manage this data, such that it always kind of you have a lot of chance of hitting in M1. And of course, this kind of prediction strategy cannot be perfect, similar to the branch predictor strategy that we talked about in the past. How we kind of predict what data going to be used in future is an information that we don't have. So we just rely on some heuristics and some algorithms to predict that, and that algorithm can never be 100% accurate, right? So that's kind of like the idea of this cache management in general. So we're going to talk about some of these challenges, and we're going to talk about some advanced solutions. Your next project is going to be also about cache replacement. So it's going to be another championship that you're going to compete against, like replacement policies and all. So to kind of formalize the notion of cache, if the cache performance can be basically shown as this formula. It's a very simple formula. It's basically what we call average access time, or AAT. So the AAT is the only thing that we care about a memory system. The memory system might have multiple levels, right? So multiple level of cache, could have a DRAM, it could have a disk, it could have multiple level of disk, and so on. What I care about from the CPU point of view is how long does it take for me to bring that data on average, right? So I want this average access time obviously to be as low as possible. If it's within few cycles, then I'm very happy as a CPU. So how do we measure this average access time? Average access time is essentially based on three important metrics. It's hit time plus the miss rate times the miss penalty. So what does it mean? Consider this as just one level of two level of a memory, right? So for example, we have just a cache and a memory, okay? So we access this data. How long does it take for data to become back? The ideal solution is that the data is in the cache, so we're gonna get it immediately. This is what we call hit time. The time it takes for us to hit in the cache, this is the hit time. So we cannot go beyond below hit time, right? So that's the most obvious case. But if the data is not in the level 1 cache, then we're gonna need to bring it from the lower cache. Let's say, for example, in this case, it's just an M2, so we need to bring the data back here. So how much time are we losing here? First, we need to check whether the data is there or not. So we're gonna always, pay the hit time penalty. And then we're gonna see how much time does it take from the system from C to M to go to bring the data. That is our miss penalty. And then the miss rate is basically saying that how often do you need to go there, right? So if your miss rate is 0, means that all the time you are hitting in the cache, which is the ideal case. If your miss rate is 100%, means that all the time you're missing in the cache and you're going to the memory. So essentially the number here is between hit time plus miss penalty versus hit time. So that's how you kind of playing with this range. You want to be closer to the hit time, and you want to be as far as possible to the miss penalty. Yeah.
Why is hit time not multiplied by a hit rate or a 1 minus miss rate?
It is actually like that. So it's kind of like this formula is kind of like this. So it's 1 minus miss rate times hit time plus it's like hit time. It's then it's miss rate then times hit time plus miss penalty. I think that's the formula. And then if you actually see this, things cancel out each other. So this one and this one cancel out. That's how you get them.
Why do we also need to hit time when we miss, I guess?
Why we need to hit time when we miss is that you always search the first cache and then go to the next one, right? So you never know, right? So you have to do the search. So this hit time is always the time for the search.
Right.
If it's there, then great. You don't need to go to the lower level. But if it's not there, you have to go to the lower level. So that's basically that's how this formula is being calculated. Okay. So the main question is, okay, how do we optimize this? And in order to optimize this, there are three options, right? You either need to improve hit time, you need to improve miss rate, or you need to improve miss penalty. There's no other thing that you can do. One of these three things or all of these three things, if you can optimize them, then you improve the average access time. How do we improve miss rate? So there's actually a whole bunch of things that you probably have learned about caches. I'm not gonna go through them because we don't have time for that, and I'm assuming that you already know that. If you don't know them, that's fine. You can always I can post a lecture of like my undergrad class on this, so kind of like basics. But maybe we can actually talk quickly about like things that we can do in order to improve the miss rate. Anyone wants any suggestion? Yeah. Better replacement policy helps you, right? So that's actually the ones that we're going to talk about today. So we're going to mainly talk about replacement policies. And as I said, it's going to be actually your CA number 3. So replacement policy obviously is one of the most important things to reduce the miss rate, because if you know what to replace and what to keep, then you can reduce the miss rate.
Increase the size.
Increase the size, yeah. So the bigger size obviously means that lower miss rate, yeah.
Like playing around with associativity and like leveraging different localities.
Yeah. So better usually like higher associativity gives you better miss rate because you have less conflict misses.
Prefetching.
Prefetching. Okay. Can you explain what is a prefetching?
Yeah, so if there's like a cache line that you know you're gonna use in the future.
Yeah.
Before like waiting until you get to that line of code and then missing, you just fetch it ahead of time, so by the time you access it.
Yes, exactly. So prefetching is this mechanism of predicting what you're gonna need in future. So think about like, you have a sequence of addresses like I plus 1, I plus 2. If I see this sequence, it's very likely that the next access is gonna be I plus 3, right? So what I can do is that when I see I plus 1, I plus 2, I plus 3, I can basically say that, okay, I'm gonna prefetch the next address. I don't need to wait for the cache to be missed and then go to the memory. I can actually, once I see I plus 2, I can bring I plus 3 as well. Of course, this is just some heuristic, some speculation. It's not gonna be always correct, but in many cases it's actually pretty accurate, right? And you can think about like, for example, things like for loop. It's obvious that why such a thing would help and would work. And then there's actually prefetching is also like very, very advanced these days. There are a whole bunch of like various different prefetchers. In fact, there's actually a championship on prefetchers as well, which we don't do, but maybe next time I'll do a championship in prefetcher as well. And prefetcher, by the way, could be hardware, could be software. So there's two options for prefetchers. Anything else? Yeah.
Well, I don't know if it's included in size, but if you have a bigger block size,
Bigger block size? So how does that help?
I mean, if you bring in, even if you bring in fewer blocks.
Uh-huh.
Your block is much bigger than.
Yeah.
Your address will match at least one of the things.
Yeah. So if you remember in cache, we had this notion of blocks. So we have a cache line and we have the block. Block means that like a combination of bunch of lines, okay? So when I bring one line, instead of just bringing that line, I can bring all the neighboring lines as well. Again, this is the anticipation of something like this, that if I need I or I plus 1, it's very likely that I need the surroundings as well, okay? This is mainly because of the spatial locality. So I usually bring like a bigger number of blocks. You want to say something, too?
Would a victim cache fall under miss rate or penalty?
Victim cache is also helps here, yes. So victim cache is this idea that if I have a cache like a level 1 and then a level 2, things gonna be kicked out from L1 to L2, right? And if I can have like a very tiny buffer, maybe like a buffer that can only holds the last 4 things, then people have shown that only like a very small buffer can help you to significantly reduce the number of cache misses in L1. Why? Because typically most of the programs work in a very small working set, which means that they only access only a few addresses at any given time. So if I only can remember the last 4 or last 8, it's very likely that I can always like remember the correct ones. Okay. Think about it as some form of an undo button that you have, right? So you can like in the last action that you have, you can always like go back to that. So victim cache kind of gives you that. And since it's small, it's not going to add much latency to the system. Okay. I'm going to show you the full list later. But let's actually talk a little bit about miss penalty as well. Any suggestions on how do we reduce the miss penalty? Yeah.
Make the cache closer
Uh-huh.
or also smaller. Like usually a smaller cache.
A smaller cache helps you, right? So a smaller cache means lower miss penalty. Although smaller cache, you can also say that it's like you're reducing hit time. So it's kind of depends on how you think about it. But yeah, smaller, lower level cache basically, right? Because the miss penalty is about like the data that you're going to bring from the next level. Yeah. More cache levels, yeah. So the whole premise of having levels is reducing the miss penalty so that you can create the hierarchy. Yeah.
Yeah, I guess, we talked before about like large higher associativity and rates. We have a direct map cache, cache takes less time to access each level.
But is that a miss penalty or is that a hit time?
Oh, that's a, sorry, that's a time.
Yeah, right. So you're gonna check quickly after. But yeah, right way of thinking, but that's just searching time. Just which is the hit time. Anything else?
I think Jake mentioned it earlier, but like physically putting them closer, like on an SOC, would improve this.
Yeah. So like you somehow like reducing the delay lines, right? So like which you can do that. This is kind of like technology, right? So it's kind of like an access time for the transistors as well. Of course, if you reduce the access time, this will be reduced. But it's more of like at the architecture level, this is not considered an architecture level optimization, right? So as an architect, you don't have that much. Yes, you can maybe like think about like where you put your cache and all, but these things mostly is decided by the VLSI designers. Anything else? Anyone M116 guys? Do you remember? We have discussed. Does anyone remember the early restart thing?
The what?
Early restart? No? Should have failed you. So for example, consider something like this, right? So let's say I have a block of 4 lines, okay? So let's say I missed a block, but I want this data, right? I want this data. So usually the way it works, since everything works in blocks, if I miss this, I'm going to say, okay, give me this block, right? So you ask your lower level to give you that block, but you only need this one, right? You only need a specific line within that block. So how do you do that? You can actually ask for this particular line first. We call it like early restart, which is like, oh, just give me this line for now. Then we kind of fill the blanks, like fill the rest of the lines in the block later, so that I can actually start early, right? So I don't need to wait for the entire block, because think about like the time it takes for this entire blocks to come back. The more data that you need to bring, the more time it takes, right? So at the minimum, you can just ask the line. You can maintain your blocking, but you can only bring that. There's another concept called soft blocking, which is also kind of similar to this, that if I have bigger blocks, but I can only like fill them in any format that I want, I don't need to like, move large blocks from different levels. I can only bring the sub blocks if I want to. All right, and the last thing is hit time. Any suggestions for hit time? Now you can say, yeah. So associativity helps, right? So something like a direct map cache definitely helps. Anything else? Yeah.
Search in parallel.
You can search in parallel, yes. Like you remember we, for example, talked about virtually indexed physically tagged cache, VIPT. That was like one way of like you search like in parallel between your TLB. Or if you have like a set associative cache of multiple ways, you can search them all together. That means that you need more search, you need to consume more power, but you can have a faster data. Anything else? Smaller cache, yeah. So you can see that how this becomes like a circular thing, right? So, bigger cache, it helps you with like miss rate, but smaller cache helps you with hit time. That's why you want hierarchy, right? So you want, for example, those sensitive ones, this latency sensitive ones needs to be small. That's why your L1 cache is really, really small and usually like a direct map cache. But then your L3 is like a 1 MB cache or 512 kilobytes of cache. And it's like multi-ways and so on and so forth. So that's how you actually make these decisions. Okay, yeah. So if you're interested, this is kind of like the full list. So we talked for miss rate, it's block size, associativity, cache size, prefetching, victim cache, replacement policy. The one that we didn't talk about was compiler. Compiler can actually also help you with miss rate because it can actually move data around such that your patterns of locality increases. Okay, so compiler actually has a huge role. For miss penalty, we have the early restarts, adding more levels, stop blocking. Write buffer is also another thing. Write buffer is mainly used for stores. So essentially for stores, you don't need to wait for the previous data to come, right? So you can actually write it into the write buffer. Hit time is associativity, as we talked about, adding more layers, parallel lookup. And then another thing that is very, very helpful for hit time is speculative loads. Remember that we said that whenever if we want to issue a load, we don't wait for the other addresses. Like if there is some form of ambiguity, we assume that there is no ambiguity and we issue it. That's where it actually helps you, right? So it's a hit time significantly increase because of that. Any questions from these? I have a full lecture on this one in case that you want to see more. I'm going to post it on Campus Wire as well. But I'm assuming that most of you kind of know the basics of the cache. That's why I'm not going through this basics. Okay, so what we want to talk about today for the rest of this class, is about some advanced cache replacement policies. And then we're going to talk a little bit about multi-core caching as well, when we actually have a system that has multiple threads, because most of these things, and most of the things that you have seen so far is about just one application and the cache hierarchy. We never talked about, okay, what happens if there are multiple applications competing for the cache space? What's the right way to kind of like have a fair and a performance systems for all of them? So we're going to talk a little bit about that as well today. Okay. So since we want to talk about replacement policy, we're basically fundamentally trying to answer this question. What do we do when the cache is full, right? And that's basically the replacement policy. What are we looking for the replacement policy? We want to maximize the hit rate, right? Or reduce the miss rate. And then what we should do, the basic idea, kind of the golden question is, can we kind of somehow magically know that what is the data that we need to keep that is the most useful data to keep? Or in other words, what's the least useful data to kick out? That's the best you can do, right? As I said, you can never achieve like 100% hit rate, but actually, yeah, if you can achieve 100% miss rate, you probably can achieve 100% hit rate as well, right? So just negate the decisions. But you can do the best, right? You can do the best you can do to achieve at least closer to that. So the obvious things first is that if there is an invalid line, you just get rid of the invalid, right? Yeah, that's no brainer because invalid lines is not going to be used. So there is no replacement policy if there is an invalid line. The replacement policy should first search for an invalid line. If you see it's there, it just like replace it with that. That's the first question. So if there's an empty spot, you just use that empty spot. But if all the spots are valid, then the question is like, what is the right algorithm to do? To answer that, there are three main questions that you need to answer, and that's what like the birth of like all of these cache replacement policies. The first is the selection algorithm, as is like which line should be selected to evict. And the second question is that okay, I kick something out and I now need to replace it with something new. Where should I put this new line? Should I put it as the most useful line? As am I predicting that this line going to be used a lot in future? So I'm kind of put it as the most recent used line or least recent used line. Should I put it somewhere in between? And then this third question is the promotion algorithm. That is, if I see a hit, if I see that this line is indeed being used, should I promote it to the highest level of usefulness? Or should I predict that, oh, this is kind of a one-time thing and maybe it's not going to be used anymore? So like maybe I can then actually demote it if I see it yet. So these are the three questions that basically is the basics of any replacement policy. This is something that you're going to also play with when you're designing your replacement policy algorithms in the next computer assignment. You're going to play with these things and say which one basically works well. That's the main thing. So there are some basic examples that you guys are already familiar with. The most famous one that you've probably seen in your classes is the least recently used algorithm, or LRU. This is what is commonly known as a kind of a very efficient algorithm. And some form of LRU is actually also implemented in real world. Although LRU itself is very expensive, we typically go with like pseudo LRU algorithms. And then like the wacky solution could be random, right? So that you don't really make any decisions, you just make all the decisions random. So let's actually talk about these, like, let's see what we do in this three scenarios. So for LRU, what do we evict?
Recently used.
Yeah, so you pick the least recently used, right? So you pick the LRU position. So you kind of maintain the recently used for every line in your set. And the one that has the lowest, the oldest line, you kick it out, right? So you kick out basically the oldest line, right? When you install, where do you put it? You put it in the most recent. So you put it as the youngest, right? And what do you do for promotion? So if you see a hit, what do you do in LRU?
Make it the youngest line.
You make it the longest line. So you also put it in the MRU, right? So that's typically like the standard LRU algorithm. For random, how do you pick the eviction? You just pick it randomly. On install, you also usually you put it randomly. And on promotion, you also to pick it randomly, although you can also play any sort of combination of this. So for example, you can do random and MRU and random and LRU and so on and so forth, right? So this is like kind of like the basic. We're gonna see what is like how we can improve this. So that the whole question that we are trying to look at in this lecture is taking LRU and try to improve LRU based on some insights that I'm going to share with you. Okay. Before that, just keep in mind that essentially any algorithm that we're going to use has this trade-offs that we need to make, right? So essentially, any sophisticated algorithm typically needs to memorize things, right? Similar way that we have branch predictors that needs to memorize things. So memorizing more things means larger latency for decision making, as well as more power and area, right? So this is a general trade-off that you need to deal with. But of course, better replacement policy gives you lower miss rate, eventually better AAT, right? Another thing that you understand is the type of misses, because this is what you are trying to prevent, right? For the replacement policy, you're trying to remove the misses. The first type of misses is what we call a compulsory miss. Compulsory means that first time I see a particular data. I haven't seen this before. That's why it's not been cached, because at the beginning of the initialization of a program, everything is in the main memory. Nothing is in the cache. You only bring things in the cache when you want to read them the first time. So the first time you see some data, it's going to be compulsory misses. Doesn't matter how how big is your cache is, what is your replacement policy, you're gonna always have the compulsory miss. The only way to get rid of compulsory miss is either you prefetch, because prefetching kind of give you this ability to bring future data even if you haven't seen them, or if you have bigger block sizes, right? If you have bigger line sizes, which means that if I bring 1, I also bring 2, 3, 4, and 5, which means that 1 gonna be a compulsory miss, but 2, 3, 4, and 5 is already loaded, right? So that's how I reduce the compulsory miss. Then I'm going to have conflict misses. Conflict misses is when the data is out because of some conflict. Okay, so think about something like this: that I have a cache set that only has 2 ways. Okay, and there are 3 addresses A, B, and C that all 3 of them map into this cache. So for example, initially I have A and B, so C is in the main memory. Okay, now let's say that, for example, the program wants to read C. What happens is that since I need to now load C, I need to decide between A and B to evict one of them. Let's say, for example, I decide I need to evict B, so I'm going to have A and C in this cache after this. Now the question is, if B comes next, then I'm going to have what we call a conflict miss, right? I kicked B out because there was a conflict with C, but if I had a better, if I have somehow I knew the future and had a better replacement policy, I could have kicked out A, and this would have been B and C. In this case, this would have been a hit, right? So better replacement policy would have prevented this B to be a miss, and it would have been a hit, right? So how do we prevent that? This is where we actually, better replacement policy comes into play. Of course, higher associativity also helps you. For example, in this case, if instead of 2, it was 4, then we could have had A, B, and C all together in this. There was no need to send out to kick out A. Then we have the capacity miss. The capacity miss is that when my cache is full, it doesn't matter how many associativity that how many ways that I have. It's still, if I had all the ways, it's still this would have been fit. So that's why we usually, in order to understand what is a capacity miss, we assume that the cache is a fully associative cache. If there is excuse me, if it's still a miss in the fully associative cache, then we call that a capacity miss because there's no conflict anymore. How do I make the capacity miss go away? By having bigger cache, or by compressing the cache, or by having some form of optimization to reduce the working set. Then I have these other less common type of misses called coherence misses. Coherence misses is because that I have a line shared between multiple threads, and one thread is kind of trying to kick out the line, and the line is also kicked out by the other threads. While if there wasn't the coherence policy, we didn't need to kick this out. For those of you who are not familiar with coherency, it's just the whole business of how we actually maintain the same data between multiple cores in a program. But we're not going to go through it, so don't worry about it that much. But it's generally when we have a multi-thread algorithm. And lastly, we have also what we call a clavariance cache misses. And this is just generally because of a bad replacement policy. So think about random misses. If you have a random replacement policy that just randomly kicks out things, if you instead of random you had an LR, you probably didn't have that problem, right? So this is type of the misses that you were trying to avoid. The last thing before I give you a little bit of break is you also need to consider different types of workload. Generally, you can consider workload as 3 groups in systems. You have either cache-friendly workloads. These are workloads that have lots of either spatial locality or excuse me, or temporal locality. They might have a small working set or a large working set. So this is the data that's kind of trying to access an array or some form of a linked list and so on and so forth. They might require a large memory, but still so much locality, or it could be a small. Then we have what we call cache unfriendly applications, which could be a thrashing algorithms. A thrashing algorithm, when you have some sequence of 1 to n all the time, but n is much, much larger than your cache size, okay? So think about, for example, that you have a large, very, very large array or a very large database that you constantly need to access things. there might be reuse, but this reuse is unfortunately like much longer than the cache size, much longer than the sequence that you can remember. And then you have a streaming applications which basically has no reuse. So essentially, if you have or didn't have a cache, it doesn't matter because there is no locality whatsoever, either spatial or temporal. And you can think about this as like watching a video, right? So or streaming data from the internet and so on. So once we have this, then we need to kind of like, understand how we should design our replacement policy. And keep in mind that applications can change phases. So for example, an application can have a cache-friendly phase, but then it becomes a streaming application. So not everything is just either streaming or cache-friendly or a small size or big size. It's actually changing. And that's a very important aspect of these systems because if it was just one, I would have chosen one application and replacement policy and call it a day. In fact, is that the diversity of the application and the difference in behavior of the application over time is the challenging part for designing any sort of replacement policy. All right, so with that, let's have a quick break and we're gonna come back and talk about how to improve LRU. Continue. Okay, so let's see what we can do. So from now on, you're gonna see lots of bip and drip and drip. So this is gonna be the names that you're gonna see. So let's see what are they. So the first question is, okay, what can we do with LRU? Anyone wants to suggest any solution before I actually give you solutions? So if I don't want to do LRU, what should I do and why?
Well, there's like you were saying, like there's rip and grip and stuff where.
So you're already familiar with those?
Yeah.
Okay, so don't say anything. Yeah.
I'll just remind you that the usefulness categories in change or something along those lines.
So you kind of like keep track of usefulness.
Yeah.
Okay, yeah. So it's kind of like LRU, but maybe like a more advanced LRU that you see what is useful. Sure. Yeah, just keep in mind that LRU itself is very, very expensive. So in practice, we never actually implement LRU itself. We implement something called pseudo LRU or tree LRU, which is basically just one bit, really. It's not even like the whole weights, like n bits. Yeah.
What's expensive about LRU?
Because for any so the two things is expensive about LRU, right? Think about like a 4-way set associative. For each one, I need to kind of store a metadata, right? I need to store basically the location, right? So if I have 4 bits, I need a log of that, whatever that is. So for example, in this case, I need to record a 2-bit value for all of them. Another thing I need to do is that I need to then update this 2-bit value every time that there is an access. So this is very expensive. Okay, so how we can fix this? The first question is, maybe it's not a good idea to, when you install a new line, put it at the most recently used. I'd put it as something that you expect to be hit again and again in future. Why? Because of this dead on arrivals lines, the DOAs. So these are the applications from spec benchmark. Remember I told you spec is kind of like the gold standard for checking the behavior. And this is the number of the amount of dead on arrival lines in these caches. So this is basically the lines that has 0 reuse, which means that you bring it to the cache, you never use it again. So as you can see, like the numbers are pretty staggering, right? So you can see, for example, for things like MCF and ART, is above 90% of the data that you bring to the cache is basically useless. So you would be significantly better off if you actually never touch the cache for these things. Yes, there are many that are like in 10% or 20%, but if you actually look at the average, you see that the average is about 50%. So what it tells you is that most of the lines that you bring to the cache, you're not gonna ever use it. Okay? So it's a terrible idea to put them as MRU. It's better to actually do maybe the opposite and put it as LRU, right? So that would be something that you can think about. The second thing is that for streaming data, this is actually a great way to kind of filter out streaming data. Because if I put everything in LRU, then streaming data is basically just kick itself out, right? So basically, if let's say, for example, I have an 8-weight set associative cache, then if, for example, this line is the line that I just brought, and I put this as LRU, and I'm using some form of an LRU, the next time I want to bring something, I kick this out and bring the new data. And then again, I kick that out and bring the new data. So this rest of this cache is going to be preserved for the other applications. Remember that you never just run one application, right? Or you run a bunch of applications. So for streaming data, this is also great. Okay. So this is what we do, right? So we actually, instead of like putting it into the MRU, we put it into the LRU position, and we call this a LIP. It's an LRU insertion policy, okay? So the difference between LRU and LIP is that instead of putting things in the MRU positions, which I normally would do, I put that at the LRU position. Okay, so everything else is the same as an LRU algorithm. So I still like use the least recently used one to kick out. But what I do is I install them as LRU instead of MRU. But it's still I promote it to MRU if I see a hit, right? So if I see a hit and say, okay, this is not a DOA, so now I need to actually properly put this as the most recently used. Excuse me. Still recovering from a cold. But in most cases, this is not going to impact my cache significantly, right? Because it's just basically just kick each other out. Okay. Can anyone point out a problem with this? Yeah.
So what if you have a workload where you're streaming, but you're alternating between two different blocks? It's gonna be awful because you're gonna stream the first block, you bring it in, okay, and then in the second block streaming, okay, that block now it makes that block you just got in. Then you go back to that first block and you just go back and forth and you just keep crashing. Even though you keep bringing it into the cache, you're instantly evicting it, even though you're about to go use it again. It's not the exact next thing you use.
Yeah. And then what should we do? So basically what it does is now it's very, very unfair to some data that might have some reuse, but not immediate, right? So we are basically kind of like, you're now on the other extreme that's saying that, okay, nothing gonna be reused. So let's put everything in MRU, and then that means that those things that might have been reused now is very, very disadvantaged, right? So what should we do?
Oh, there's
Yeah.
Second least recently used.
Maybe put it as second, right? So second is a great idea, right? Any other suggestion? Sure.
somewhere in the middle.
Somewhere in the middle is kind of like second, yeah?
If you don't wanna use like more bits, then you could maybe sometimes put it at MRU and sometimes LRU. So if you have like a frequent pattern where you're like prone to crashing, at some point you'll get it right and you'll stop.
That's exactly what we do. It's called BIP, or a bimodal insertion policy. So the bimodal insertion policy basically tells you that if you have the decision, like a binary decision, right? So for example, put it at LRU or put it at MRU. Let's flip a coin, for example, and based on flipping the coin, decide. Okay, so sometimes put it at MRU and sometimes put it at LRU, right? So basically think about it as something like this, that you define an epsilon, and this epsilon is some predefined parameter. You query a random number, you see if it's like smaller than epsilon. If it is, you put it at MRU. Otherwise, you put it at LRU. Okay. So this epsilon could be, for example, 50%. So in like half the time you put at MRU, half the time you put at LRU. Typically, you want this number to be skewy toward one of the directions, right? So typically, I think this is a much smaller than 50%. So you want to put most of the things at LRU actually. And as I said, the reason that you want to do this is that you don't want to be very, very unfair to some of the lines that they want to be reused. So you want to have some form of a balance, right? And this BIP is going to give you a balance for that. Questions here? Cool. So what is the problem with BIP? How we can improve BIP?
Because it's random, we're not really making a smart decision. Like, how do we know which is the right thing to do? Like, how do we choose our throttle parameter?
Okay. Anything else? It's good. It's actually, we have a solution for that. Any other suggestions? Yeah.
I mean, it's still a low percent chance that you put it the most recently used. So if you're not in a streaming workload, it's still like way worse than LRU.
Okay. So
Also epsilon's like a fixed parameter string. Different parts of your code might be better suited for different values.
Okay, so if you can also somehow make this epsilon some form of a dynamic number. Okay. Good points. And then somebody already said that you don't want to just MRU and LRU, right? You want to just maybe have like a second or somewhere in the middle, as Jerry said, right? So those are also solutions. And that's exactly what we are doing, right? So one thing we are seeing is that BIP is great when you have some form of a streaming applications, or some form of a mixture of a streaming application and cache-friendly application. But if you have a really cache-friendly application, then BIP is also reducing your performance, right? Because even though the epsilon is small, but still putting some of the things at the MRU position that you don't like, right? So the question is, can I somehow dynamically choose and know that this application is a cache-friendly application? So let's just continue with the regular LRU. And this application is a streaming application. So now let's actually do BIP, right? So this is, I need to somehow know this. And for example, I can use some form of a compiler trick or some form of a user-defined tricks to kind of notify the hardware. And that's actually some solutions does that. But in most cases, I need to know this dynamically because there's nothing that you can know beforehand. So the idea is that how can I do this dynamically? And this is very common in many solutions in computer architecture, that you have a bunch of different solutions. Each one works well for some particular case, but there's no like a one size fit all kind of solution. So in order to make this decision dynamically, you kind of go with this hybrid or tournament-based predictors, which you have this and that. You kind of like, query both, see which one is better, you choose that one, okay? So this is kind of like the idea of a hybrid method, right? So can I basically choose the best policy during the runtime? So what are the ingredients? What are the main things that I want for being able to implement that? So of course, I need to some form of an estimation of each one because I need to decide, right, which one is better. So I need to be able to say that, okay, this is the performance of this one, this is the performance of the other one. Then of course, I need a policy to enforce the better one. So I need a mechanism for that. And then I need to apply that to the rest of the cache, right? So this is what we need to do. So in order to do that, there is this method called auxiliary tag directory, ATD. Think about it as like instead of like, having only LRU metadata, I have LRU metadata and also have metadata for BIP, right? So what I do is that, let's say I have a set. And then what I can do is that think about it as kind of like I duplicate this cache. I don't need to duplicate the data. I only duplicate the tags. Okay. So I have the same tag, but this time I apply BIP to this. Okay. So I apply BIP to this. I apply LRU to this, and then see which one is gonna give me a hit next time. Right. So I kind of like think about it as maintaining two replacement policy at the same time. Then what I'm going to do is that whichever is performing better, I'm going to choose that for the rest of the cache. Okay. So for example, I can do this for a large portion of the cache and then apply to the rest of the cache. I can apply this. I can use this for all the lines in the cache and so on and so forth. Well, of course, if I want to do this for all the lines, it's going to be very expensive, right? So I need to somehow kind of like decide some form of a dynamic mechanism that only choose a subset, and based on that subset, it basically applies it to the rest of the system. So this is, first of all, here's how this A to D idea will work. So I have two sets, set one and set two. I have data for one replacement policy, data for the other replacement policy. I have some form of a counter. Okay, and then based on the counter, they're gonna apply that to the rest of the cache, to other sets. Okay, so if both of them gives me a hit, I'm not gonna change the counter. If both of them are gonna be a miss, I'm not gonna change the counter. If one gonna be a hit and the other one gonna be a miss, I'm gonna increment the counter and then vice versa. And then what I do is that basically I look at the sign bits, right? If the sign bit is a positive number, means that this one is performing better than this one. If the sign is a negative number, then that means that this one is performing better than the other one, right? So I basically look at the sign, and the sign is the policy that I'm going to apply to the rest of the cache, right? So there are overhead, right? Because now I need 2 tags and 1 counter per set, which is very, very expensive. Okay. So how do we optimize this? We do 2 things. First of all, I don't need like 1 counter per set. First thing that I can do is that I can have only 1 counter that kind of like reads it from all the set. Right? And then only use this for then the rest of the cache. So just 1 counter would be enough. I don't need to like have per set counter. The second thing is we can only sample few sets. Okay. So the idea is that if the sets are behaving randomly, so there's no like a difference between set A versus set B versus set C, what I can do is that I can say that, okay, I'm only looking at the behavior of set B and set E. Okay. And whatever happens for these 2 guys, I'm going to apply to A, C, D, E, F, G, H, and so on and so forth. Okay. So essentially, this is what we call a dynamic set sampling, DSS. DSS means that I don't need a separate counter, and I don't need to look at all the sets to make a decision. I just only look at the subset, and very, very small subset actually. And based on that, I can basically make a decision for the rest of the cache. Why this would work? Because essentially there is no particular differences between these sets in terms of behavior. All of them perform fairly similarly because essentially there is no particular bias toward any of the sets in terms of address, because addresses are generated randomly. Different programs generate different sets randomly, and everything is kind of a random distribution. As a result, I can just pick random sets and it works. And in fact, people have shown that this works very well in practice because of this. On average, works really well. Does that make sense? Cool. Yeah, so this is called dynamic set sampling. People actually shown that with only 32 sample sets for a 1,000 set size cache, this will give you like good results. There's actually some analytical tests and results for it as well. It's basically, interestingly, it's like very simple, similar to the birthday paradox problem. So it's kind of like they show that this is how this can be reduced to the birthday paradox problem. And that's how they come up with like much smaller number. Yeah.
So for this, how do you usually choose which sets you're gonna sample? Is it static? I mean, that's the dynamic set sampling. Is it like random every time you choose random ones each time?
Well, so it depends on how you implement this. If you implement it in software, yes, you can then dynamically choose. The reason that it's called dynamic is because your replacement policy is dynamic, right? So depending on how these particular sample set is behaving, then you might use BIP or LRU. That's why it's called dynamic. But usually the sets that you're looking at is going to be static because you need this ATD for them, right? So you need to actually have extra logic and all that. You need to actually implement this in real hardware.
So these sets, so you're testing 2 different replacement policies here, right?
Yeah.
How do you test both of them? You have a small subset where you do both,
Yes.
and it's just for like this small sampling set.
Yes.
So like you have like a separate, like you do your.
Think about it as you have 2 sets, right? So B is basically 2 Bs, like B and B prime.
Like what is ATDX and ATDY? Or like.
So ATDX is policy X, ATDY is policy Y.
So isn't there already 2 right there then?
So the figure is a little bit confusing. So initially I need a full copy of both, right? So I need, let's say if I want to apply to all the sets, I need a full set of AB all the way to F for policy X. And I need the same, like a replicate of that for policy Y. What we are suggesting is that you only need this kind of these. That's the only thing that you need. You don't need the gray ones. Okay, so essentially you have B and E, and you replicate B and E on the other side as well. Make sense?
And then you test how well they're doing.
Yes. So using this counter, right? So if both are miss, you don't touch the counter. If both are hits, you don't touch the counter. If one is miss and one is hit, then that's when you change the counter.
And then you're gonna change the policy for the whole cache.
Yes, so the most significant bit of this counter then applies to the rest of the cache.
How big is the counter? Is there a general size?
So there are papers that talk about the specific implementation of it. I think it's probably something like 16 bits and all, that should be more than that. And it needs to be a saturating counter, right? Because if it's saturated, you don't want to wrap around, because wrapping around means that your resetting is terrible, right? So it's saturating, yeah.
So if, for example, if like Y says it's hit it's a miss, so
Mm-hmm.
you're actually gonna like replace, do whatever like the replacement policy does, like bring the data to the cache.
Mm-hmm.
And but X said it's a hit, so you don't do anything to that.
So to those sampling lines, so these ones that are you're monitoring, you apply the replacement policy directly to them, whichever it is. So for this one, you apply X. For this one, you apply Y. For the rest of the cache, you apply the winner, whichever it is.
Yeah.
So if it says BIP, if you want to replace, you use BIP to replace. If it says LRU, you use LRU to replace. Make sense?
Yeah.
Yeah.
Couple questions. So one, can this be extended? Is this extended to like more than two? If you have 4 and you just take the greatest?
Is this applicable to more than 2? It might be. I don't think anyone has tested this, as far as I know. I haven't seen anything that tested this for more than 2. But you technically can, if you have like, counters. You need to like probably do like 2-way counters and 4-way counters and 3-way counters and all that. So it's gonna be fairly complex. That's why I'm guessing that it's
like, oh, if this one's right, then like everyone else gets decremented.
Yeah.
And you get.
Something like that, like a tag-based kind of like
Okay,
situation. Yeah.
At what point is this all like happening in, let's say, any kind of like workflow? Like, because I know that this requires like all the data to be in, like the cache to be loaded with stuff, and you can have like a certain point to test it out. So when does that happen?
So when we're kind of like the system is warmed up.
Okay.
So like, at some point in the middle of the program, the system will be warmed up and you can see this. This generally has a lag, right? So for like, if your workload changes, it takes some time for your counter to pick it up. But generally, if the counter is not too big, then after a few misses, it's going to catch up. So over the long term, this is going to work very well. Yeah, so if you look at the do the plug in the numbers, you're gonna see that basically your overhead gonna be 2 to 3%, which is very reasonable for a system like this. Okay, so this is basically called DIP. Okay, a dynamic insertion policy. That we have 2 type of workloads. Let's say, for example, an LRU and a BIP, and we use DSS to pick between the 2. Okay. And then essentially what it does is that monitors both LRU and BIP, choose the best performing policy and apply that policy to the rest of the cache. And as I said, we don't need to look at the entire sets. We just randomly pick 32 of them, very small subset. Look at that, and that would be basically applies to the rest of the cache. Okay. This is kind of like, if you want to see kind of like the implementation of this, you have some LRU sets, you have some BIP sets, you have some counter, and then you have what we call a follower sets. And these follower sets are basically, whatever these 2 guys decide will be applied to these guys. Okay. And this is kind of like the implementation of it if you're interested. All right. So what is the problem with DIP? Anyone wants to improve DIP? Yeah.
So it kind of is only for the whole program, right? And what if you have a streaming application with mixing in some reuse, so like regular cache non-streaming, right? So it kind of only, we're only working for like situations where your program is going through phases.
Mhm.
Like, oh, it's a streaming workload, okay, now we're gonna switch to the regular workload, back to streaming.
Mhm.
But with this, it doesn't work for mixed workloads. So you're either gonna be in the like thinking you're gonna be the streaming one, or you're gonna be this one. So you want
More granularity, right?
for different addresses.
Yeah. So that's kind of like along the lines. So essentially, you want a little bit more granularity than just saying that, okay, this is either BIP or LRU, maybe something in between. That's one thing. The second thing is, if you go back to this, we talked about what should we do when we install a new line, and this BIP and LRU basically fixing this, right? But there's also the other two things that you can do. One is, well, what to select to a big, and one's very important is that what should I do on a hit? Okay, how much should I promote? So to understand that, as I said, first of all, let's revisit LRU. LRU, the way it works is that we have some form of a metadata or timestamp, right? So we, if you have like an n way set associative, I need log of that in order to pick that, all right? So like, to store that, and I need to update this for every single access and so on and so forth. In reality, as I said, we typically don't implement LRU in real systems. We implement pseudo LRU, or called PLRU. Excuse me. PLRU is usually implemented two ways. There are both implementation in real world. There's one called 3LRU or TLRU, and there's another one called NRU. What is NRU? So NRU is like something like this. NRU is basically just using one bit. It's called not recently used, okay? So NRU works like this. In LRU, you have the most recently used location and least recently used location. In NRU, you only have a bit, a flag, okay? A flag is initially 1. If it's being used, then you put the flag equal to 0. Excuse me. So essentially, the algorithm is like this: that on a cache hit, you set the block to set that line to 0, which means that now. So if it's 1, it means that not used. If it's 0, it means that it is used. Okay. And then when we have a cache miss, basically the way it works is that you want to go and find the first one that is 1, right? So the zeros are good, right? The zeros are the ones that are being used. You want to find the one that is 1. If you can find that is 1, you kick that out. So for example, in this case, I kick this out because this is 1, right? In this case, I go with like this one and so on and so forth. So the idea of the NRU is that I don't need to like have like a very fine-grained bits to figure out what is the least recently used, because least recently used means the only thing I need to know is that what are the others that have been used. The one that's not being used is the least recently used, right? And then there's some other details about NRU. For example, what would happen if all of these guys are 0? So for example, in this case, what should I do? The idea here is that if I see all zeros, I'm going to reset all of them to 1, okay? And then I'm going to pick the first one, the leftmost one. In this case, I see all of these as zeros. I put them all equal to 1. Then I pick the first one, I replace it. So in this case, as you can see, A1 is kicked out and is replaced with B3. And then the rest of them are actually 1, 1, 1. Another important thing about NRU is when I insert a new line, I use the use bit to 0. So I promote it to 0 the moment that I install it. Yeah, and that's kind of like it for the NR. Any questions? Yeah.
Yeah, I'm curious why we choose the most left one.
When all of them are zeros, it's just like an implementation. So we just start with the leftmost one. You can also choose a random one. Doesn't matter. It's just very simple to do it this way. Mm-hmm. Okay, so this is the NRU. Why do I want to use NRU instead of LRU? First of all, NRU is not better than LRU in terms of performance. But it's much simpler, and it's very cost efficient, right? Because I just use one bit, and the access is also very simple. It just like zeros out the bits and so on and so forth. But so the problem with NRU though is that I lose a lot of granularity that I have with LRU. So it's kind of now the question is there something in between these two that I can use? And this is the idea of a RIP. RIP is called re-reference internal insertion policy. What it does is basically this: is that instead of having just one bit, let's have a compromise. So not have like a big LRU bits, but let's have 2 bits, okay? And then this gives you a little bit flexibility on where you put things, okay? And what you do on hits. So here's what RIP does. So this is called static RIP or strip. So static RIP, it basically does it this way. That if it wants to insert something, it insert it at 2. It doesn't insert it at 3, insert it at 2. Okay. If it wants to promote something, it promotes it to 0. So it's similar to NRU, right? So 0 means that it's been used. 3 means that it hasn't been used. So when we install something, we don't install it at 3 because we want to give it some chance to survive. That's why we put it at 2. But when it's a hit, we're going to immediately promote it to a useful. And when we want to evict, we evict a line that is a 3. Okay? So that's how we actually evict a line. If there is no line that is a 3, then what we do is that we age all the lines, which means that we increment all the lines by 1. Okay, so 0 becomes 1, 1 becomes 2, 2 becomes 3. So we will find it. If we don't find another 3, we keep doing it until we find one, right? So if, for example, somewhere like here you see that 0, 0, 2, 2, then what we do is that we increment them and then we replace them with one of the 3. So this one is being kicked out because this becomes 3. And replace it with this B3. This one becomes 3, this one becomes 1, becomes 2. And remember, when we installing a new line, we install it as a 2. Okay? So the next time I need to basically kick something out, I will kick this out. And then replace it with, as you can see, with B4. Okay? So that's kind of the idea of a strip. Any question?
Why would you want to like increment everything in the line instead of just picking whichever one has the max? Like, why do you want to manipulate the ages of all of these?
Because you want to also have some notion of like everything is aging such that so you want to show you want to also remember that okay, no one is having a priority. So at some point everybody should be kicked out. Otherwise, like they stay always 0 and never been kicked out, right? So you want to age them so that they get closer and closer to be kicked out. Yeah.
I think I think the answer to that question, it's just like, this is the only time when they age. They don't age anywhere else.
Yeah. So as I said, yeah. So if you don't age them, then they will stay forever at 0 and they never be kicked out. And the idea is that you kind of like age them and then the others will be replaced and eventually it becomes an LRU. So it's kind of a de facto LRU in some ways. Any other questions? Cool. So now the question about strip is, should I apply all those ideas that we have with LRU and BIP? And the answer to that is yes. So we can actually have BRIP. What is BRIP? The BRIP is if I want to install most of the line at 2 and then some of the lines at 1. Why do I want to do that? The same reason that we did it for streaming applications, right? So you want some lines to have more chance to survive and some lines to have less chance to survive. So that's why we usually do 2 and 1, okay? How do we do that? Exact same way that we did it in the past. We query a random number. If it's less than epsilon, we put it at 1. If it's bigger than epsilon, we put it at 2. Okay, so everything else stays the same. Okay, and lastly, you might wonder, okay, is there any drip? And the answer is yes. So if you can actually combine strip with drip, you're gonna get a drip. Okay, so what is drip? Drip is basically using the set sampling to decide whether it's a good idea to use strip or whether it's a good idea to use drip. Okay, and that will give you a drip. You can also think about this as I can have strip and lip or strip and bip, right? So like the insertion policy of LRU, or I can have strip and LRU and so on and so forth. So I can have any combination of these, but of course you have to keep in mind that strip, for example, and LRU work fundamentally different. One has like only one bit and LRU has different bits. So there is also these implementations that you need to take care of. Yeah.
So it seems like all these algorithms, you're either like switching between you think it's streaming
Mhm.
or you think it's not streaming.
Sort of. Well, it's not.
Phase of the
It's
program.
you think that it's going to be reused or not reused. That's the only
But, yeah,
thing.
but you're going through the phases of your, it's like you're thinking it's either gonna be reused or not reused for the next phase of the program, right?
Mhm.
But what about like programs that you have, you're streaming, but then you're also, while you're streaming, you're reusing some like specific stuff, and what if that conflicts? Is there,
So what
there-
you're saying is that some addresses are streaming
Yeah.
and some other addresses are
using
not
them at the
streaming.
same time?
Mhm. So that should be captured by this
How
exactly,
do you
right?
document it?
Because those that are streaming, it's going to be hopefully it's going to be captured by the BRIP base. So it's going to be inserted at 2. They're not gonna see much reuse. So eventually they're gonna age to 3 and they're gonna be kicked out. Those that are gonna see reuse, they're gonna be inserted at 2, but they're gonna immediately be promoted to 0, and then they're gonna stay there for some
What if they
time.
don't get promoted in time?
Well, that's the idea. You have a little bit time, right? So that's why you put it at 2, and now with BRIP, you even put it at 1. So if you get lucky with those lines, they actually been put at 1.
Okay, but let's say you're like more heavy on the streaming side, right? But you have some reuse.
Yeah, then in that case, you have to adjust your
Beyond strip.
epsilon, right? And then that's why you actually have drip, because drip gives you the combination of drip and strip.
But if you're mostly on the streaming side, won't the drip always just say, okay, we're using the static one?
Yes.
'Cause-
You use so again, even if you use the static one, you still have a chance to survive because you put it at this position. You don't put it at this position, right?
Yeah, but like, okay, let's say you put it at that position and the streaming workload happens so that it always gets kicked out and you're always missing it.
Yeah, but you're saying that there's a mixture, right?
Yeah.
So if there's a mixture, there's some of these guys that are gonna promote. So not all of them gonna be killed.
Well, like I'm saying, like in the application where like you bring it in, right, and
Mm-hmm.
you stream 4 more,
Yeah.
and then so that one gets kicked. So the one you brought in gets kicked out, and you go back to it, and
Mhm.
it already got kicked out, and you just keep doing that over and over again.
Yeah. Mhm.
But there's this thing will kind of fail on that, right?
To some degree, yes. So of course, first of all, you're not gonna get like perfect answer, perfect replacement policy. But what you're saying is that there are some of these guys that never gonna be reused and needs to be kicked out. There are some of these guys that needs to be promoted, right? And how do we decide that? That's what I'm saying. That essentially strip gonna give you that because essentially strip gonna say that there's a tiny bit of chance
What about
that your thing is gonna be hit and gonna move up.
so what about like address based
Mhm.
prediction? How does that like compare normally to this?
You can do address space. You can also first of all, this set sampling, you can, for example, also do it. But just keep in mind that the address space is also completely random, right? So there is no guarantee that this address versus this address is going to be the same. But what you're suggesting is that, let me look at like a particular address and apply very specific policy to that. So same way that you do it for like a branch prediction.
Yeah.
But in that case, then you need like an address space insertion policy, which is like you have thousands and thousands of addresses. So it's going to be huge.
Well, it's similar, right? You like look at the history.
For branches is much less because for branches you have lots of locality in terms of addresses. For caches, you're not gonna have that. Because the caches is like you have a much bigger range. That's the difference.
Because there's more caches than branches. There's more cache lines than
There's more cache lines than the branches that you have. Yes,
Okay.
yes. Good. Is there more? Yes, there are more. There's another one called pip. What it does is basically the way that it promotes is different. So if you are actually interested, take a look, but there's a whole bunch of them. And I think you're gonna actually learn about them when you're doing the cache replacement policy championship. Okay. The second part of this is about multi-core. Next time I'm gonna talk about that. Okay. Next time means like Wednesday gonna be presentations, but the next Monday. Okay.
Yeah.
Thank you.